Okay, so today we are very honored to have Professor René Vidal speak at our distinguished seminar, jointly hosted by UCSD and TILOS, where TILOS is our NSF National AI Institute led by UC San Diego. Professor René Vidal is the Penn Integrates Knowledge and Radcliffe University Professor of Electrical and Systems Engineering and Radiology at the University of Pennsylvania, where he directs the Center for Innovation in Data Engineering and Science and serves as a co-chair of Penn AI. He is also an Amazon Scholar, affiliated chief scientist at NORS, and former associate editor-in-chief of IEEE Transactions on Pattern Analysis and Machine Intelligence. Professor Vidal's research advanced the mathematical foundations of deep learning and trustworthy AI, with broad impacts across computer vision and biomedical data science. His contributions have been recognized with major honors, including the IEEE Edward McCloskey Technical Achievement Award, which is for recognizing his pioneering contributions to subspace clustering and generalized PCA with applications in computer vision. The Allenberg Faculty Awards, the J.K. Agarwal Prize, for recognizing his substantial contributions and major impact on the field of pattern recognition. The O.N.R. Young Investigator Awards, the NSF Career Awards, and multiple Best Paper Awards in machine learning, computer vision, signal processing, control, and medical robotics. He is a fellow of ACM, AIMBE, IEEE, and IAPR. He is also a Stone Fellow. Today, he will be sharing with us his insights on how to build interpretable and faithful AI systems. Without further ado, let's welcome Professor Vidal.
Thank you, Lily, for such a great introduction, and thank you all for coming. I've been here many times, but it's always great to be back. I think the first time was 2003, and I remember being with Nuno and Sanjoy, and I think I spoke about representation learning and generalized principal component analysis and things like that at the time. I came a second time. Zhuoden invited me to speak about computer vision. I think Nuno and I were doing a lot of work on action recognition and dynamic textures at the same time. So that was probably the second time I visited. I work on many things. Some of them are purely theoretical, and that shares my passion with Misha for the theory of deep learning, and we run into each other often. Others are biomedical, and so I had a great meeting with this morning about that. Others are really computer vision, but today I am going to speak about what about 5 of my students are working right now, which is trustworthy AI. I've worked a lot in questions of robustness, safety, and interpretability over the last 5 years, and that's primarily what I intend to talk about today. The motivation for it is we know that AI is working extremely well, and when it begins working in high-stake applications like medicine or a self-driving car, we have to worry about whether it's working or not and why. And 2 important questions show up. One is, what is the model doing? Why? Can I understand why it made the prediction it did? And the big problem is that most of the models are black box. So when they work, we don't necessarily know why they work. And when they fail, we don't necessarily know why they fail. So the question of interpretability is important, not always. Not every machine learning model needs to be interpretable, but some of them do. The second part of the talk will focus specifically on LLMs, and specifically on the question of safety and how do we ensure that the responses of LLMs are well aligned with human values. As an example, imagine the question of toxicity and how do you automatically make sure that the responses of LLMs are non-toxic. So let me get started directly with the first topic. So as I was saying, most machine learning models are black box. But in medicine, as a matter of example, you would like to have a model that given an MRI scan, predicts that the patient has Alzheimer's. But if it is a black box and if it says 98.6% that you have Alzheimer's, probably you want to know why. Or why can you tell from that image that that patient has Alzheimer's? And more likely than not, you might be interested in having an explanation about the anatomy. Like, I don't know, there is atrophy in the amygdala in the brain, might be one potential explanation. Maybe it's not sufficient, but at least a partial reason as to why that was the case. This has motivated for the last 10 or 15 years a large body of work on what is called post hoc explainability. That means you take a high-performing model, and then you try to explain what are the features that this model paid attention to. In the case of computer vision and medical imaging, typically this means what are the regions of the image or what are the pixels that were responsible for that prediction. And this is a list of some classical methods like LIME and GradCam and SHAP. The reason people do that, the good thing about this approach is that you're taking a model that is high performant, the one that you're actually going to use, and then trying to explain what is it that it did. But there is just a body of literature trying to say that this approach makes no sense. Just to provide one example as to why it doesn't make sense in this case, well, think about the skull here. Think about, the red regions are highly important, blue regions are not very important. And you're predicting that the patient has Alzheimer's. Look, there are many regions that are red that are even outside the skull. So the problem is that we get regions that don't make sense. And we now, as users, begin debating, why did it pick this region? Why didn't it pick this other one? And so this has motivated many people to say that you should be far more worried when you hear that an explainable AI method has been deployed in a hospital than when you hear that it hasn't. And the reason is these methods are actually pretty much nonsense. And without causality as to A implies B, I think it's very hard to make sense as to why that region in the image is an actual explanation for that prediction B. So many, including me, have been advocating that one potential approach to deal with this is to develop methods that are interpretable by design or intrinsically explainable. And a fundamental problem I see is that as a community, we have not come up with a definition of what interpretability or explainability means. If we look at neighboring communities like privacy, at least they came up with a definition called differentiable privacy. And what this means is that if I write a paper about privacy, I will probably check the performance of my method against that definition. What's been happening in explainability is that every method says, this is my algorithm for explainability, and these are my results, and these are better than the previous ones. But we don't necessarily agree that it's the same definition, so we're comparing apples to oranges. While I don't have, and I'm not going to propose or claim that I have a definition of explainability, I will propose one in a moment, and I'm not claiming that it needs to be done that way. At least I'd like to say a few features that I think explainability should have. The first one is, who are we explaining this method for? And I will concentrate on a particular kind of explainability that is explainability for the user of the AI system. The layman, not the person that knows AI. Okay. And so a user, more likely than not, would like explanations that are in terms of language. If a self-driving car has an accident and we need to decide who pays for the insurance, more likely than not, we're going to ask, did you stop? Did you not? Did you turn right? Did you see the pedestrian? Why didn't you do this? Why didn't you do that? So all those explanations to decide who will pay the insurance will probably be in the form of language. Or more generally, patterns that are understandable to a human in the data. Second, I'll argue that therefore, explanations need to be domain dependent. The explanations will be, say, on language that is pertinent to that task, pertinent to that domain. And third, I would argue that explanations are dependent on the user. Let me give you one concrete example. I am a clinician. I take a bunch of tests over a patient, I decide on a certain diagnosis. I need to explain that diagnosis now to another clinician. I will use certain words because I know the other person is an expert. But if I have to do an explanation for the same decision, same patient, same data, but I'm going to explain that to the patient, I'm probably going to use a different explanation that is adapted to the user. So that's what I mean here by explanations are user, task, and domain dependent. So how could we possibly capture all of these ingredients into a potential definition, at least, of what explainability might be? So in the work that I'll be presenting today, we capture that based on what we call a query set. A query set is a set of questions about the data. So on the left, if the task is classifying birds based on images, these queries might typically be about attributes or body parts. Is the belly yellow? Is the beak elongated? And so on and so forth. On the far right, if the task is medical diagnosis, well, by and large, every time you go to the doctor, the first thing they do is they ask you for a sequence of symptoms. Do you have fever? Do you have a sore throat? Are you coughing? Do you have congestion? And based on this sequence of questions and answers, they will decide on what is the next question, the next test, and they will begin entertaining hypotheses as to what you might have and eventually narrow it down to what disease you might have, perhaps requiring additional queries in the form of you need an MRI scan. So specifically, the framework that we have developed over the last 5 years is an information theoretic framework about explainability. And this framework is called information pursuit. And this framework, as I'll advocate in a moment, has strong connections to information theory, but it's actually based on a very classical algorithm from the 1980s, 1990s, called information gain, or actually based on many games that we play as humans, like 20 questions. So 20 questions, raise your hand. Have you played 20 questions once in your life? Yes, many. Okay, let me play 20 questions with you. I have a number in my head from 1 to 10. Your goal is to guess the number. Ask me a question. Any of you, ask me a question. 5. Is it larger than 5? Okay. Any other has another question? Huh? Even or odd? Any other question? Okay. Good. Let me begin with, is it even and odd? Let's say that I said is even. What would you ask me next?
Then larger than 5.
Okay. Let's say I go with your question. Yes, it is larger than 5. What's your next question? 7. Yes. Next question. Yes. Okay. Maybe not optimal. So you can guess, and I'm going to say yes, yes, yes to each one. With 4 questions, you can get it, and you're going to guess that it's a number 10. And what this means is that how did you select, and I play this with my 10-year-old, he's 13 now, but he also said, is it bigger than 5? And I asked him, why did you ask me that question? And he is not a computer scientist or anything, right? He's a 10-year-old, but he sort of said in his own words something like, well, it splits the space half and half, right? And that's why you select, so that's why this bigger than 7 is better than even or odd, because it's just maybe repeatable. It's the same style of questions, you continue. But the long story short is that once I told you, yes, it's bigger than 5, of the 10 possibilities that you had at the beginning, they get reduced to just 5 of them or 4, right? And therefore, you can also make predictions as to what number it is, and the number of possibilities keep reducing with every question. So the idea is to do the same. Suppose that I had this bird classification task. And if you're an expert on bird classification, that I'm not, what would happen is that they will be able to classify what bird it is based on a very small number of features, and there is typically a one-to-one correspondence between these features and the class of the bird. This example that is shown here is an actual running of the information pursuit algorithm that I'm about to describe, where what it does is it selects, in this particular case, only 7 questions. So is the shape Pershing-like? Yes. Is the bill shape all-purpose? Yes. And so based on these 7 questions only, out of, in this case, for this data set, there were 300 possibilities. it's able to predict this is a green jay with 99% probability. In this framework, by the way, what is the classifier and where is it? The classifier never gets to see the image. The classifier only gets this sequence of questions and answers and predicts the bird only based on the sequence of questions and answers. So, is the explanation faithful? Yes. Here, the prediction, the green jay, is a function of the explanation, which is this sequence of questions and answers. And so the explanation is faithful by construction, and this is a classifier that is explainable by design because I tell you this is a green jay because of these 7 reasons that are here. How do we do this? We need 3 main ingredients. The first one is, where do I get the questions? The second one is, if I have a set of questions, how do I answer them for an image? The last one is, and this is the more theoretically important and fun for me, is what is the algorithm to actually select what questions to ask and in what order? So for the first part, what was done a couple of years ago was simply begin with, I have a fully annotated data set, like the set of birds. There were 200 classes of birds, 300 attributes. Each image was annotated with every attribute. So you could actually train a neural network that predicts the attributes of the bird from an image. That led to the concept bottleneck approach that you predict all of the attributes and then you put a classifier on top. The issue with that is that you need to predefine a priori your query set. And also, you're not adaptive. You cannot answer new questions. And so a second approach that is a little bit more flexible and that was enabled by LLMs is to, let's say I wanted to do this for ImageNet. You can simply say, hey, LLM, here is the ImageNet data set, has 1,000 categories. For each category, give me the 10 most important visual attributes. And now I can take the union of all of those attributes across all the classes and build using NLP tools a query set. So this is possible today. If you truly want explainability for the user, you would say, hey, user, what is the set of questions that if I am able to answer would make this algorithm explainable to you? Okay, so that is the way we would do it user dependent. Second part, how do we answer the questions? So at one end, you could say, well, let me take your latest and greatest foundation model. I can input an image, I can input a question, and maybe they're very good. Maybe today they're very good. Maybe in 2 years, they're going to be perfect. So just get a visual question answering system. I think probably that's going to be the case, but within this overall framework of training a system that is going to select what question to ask in what order and being efficient, these methods are too slow. And so we wanted something that was very efficient. I want to get the answer to those questions very efficiently because I need to answer questions for every image and the number of questions could be large, the number of images could be large. So the other extreme, which is on the left, is CLIP. I'm assuming all of you are familiar with CLIP, but if you're not, you could say, take your question, embed it into some vector. Take your image, embed it into some vector. What CLIP does is that there is a high level of alignment in these 2 vectors if the text is a caption for the image. So you expect the dot product to be high if the answer is yes. You expect the dot product to be low if the answer is no. The reality is that if you look at data and you look at the distribution of clip dot products between images and questions, rather than either being 0 for the answer being no and 1 for the answer being yes, it's a Gaussian center at 0.5. So clip dot products are absolutely useless for as a visual question answering system. Okay, maybe they're very useful for the very specific kinds of things where CLIP was trained, but they're not very good for anything fine grain or out of distribution. Like the bird example was one example for which CLIP is actually really bad. So what my students did was something incredibly practical based on very simple ideas, which is that you can actually train a 3-layer MLP to perform very well at visual question answering by combining GPT and CLIP to produce pseudo-labels. Let me be very concrete here. Suppose that, as I said, you've got your big data set, ImageNet. Suppose that you've come up with an LLM that provided you 10,000 questions. You have no annotations. You don't know the answers to these questions, right? And you don't want to use humans to produce the labels. It turns out that if you ask GPT a question for which you don't need the image, like, does the dog have fins? GPT is very good at, in this case, saying no, right? The dog does not have fins. I don't need to look at any image to know that a dog does not have fins. So you trust GPT for these questions. But if GPT says yes, then you're not sure. Let me give you one example. Does the dog have a leash? In that case, you need to look at the image because not every dog has a leash, right? And so what we did here was simply via this combination of GPT and CLIP, is like we take GPT, we give the question, we give the class. If GPT says no, then we say the answer to the question is false. If GPT says yes, only then we take the dot product of CLIP embeddings. And we prove that condition on GPT, we did not prove. We showed experimentally that condition on GPT saying yes, the distribution of CLIP dot products becomes more bimodal, and therefore you can have answers of yes or no. So with that now, we have pseudo answers for any new data set that you want. And with that, we can train this 3-layer MLP that does way better than CLIP and almost as good as Lava or Blip, but in a fraction of the time. Okay, so in that way, we build a very lightweight visual question answering system that works well. Here is actually concretely what happens. So take ImageNet as one example. Take the accuracy of CLIP dot products is like 50% at answering questions, yes or no. Take Blip. Okay, today this is not a large model, but at the time this paper was written, that was one of the largest models. So the accuracy was, for the largest model, was 0.86. So with this super simple 3-layer MLP, we got 0.87, so about the same. And the time it takes is 0.04 seconds per query versus 1.52. Okay. So hopefully this table across many data sets tells you that this very simple VQA system is not the best, but is very decent to be used in this online fashion, which is what I need to do next. Okay, so I've told you how we're going to come up with the questions, and I've told you that we have a simple VQA system to answer them. Let me get to the part that is now fun, I think, to me, which is how do we implement this information theoretic framework for explainability that automatically select what questions to ask and in what order? Okay, so this is going to be the part of the talk that has a little bit of equation, so maybe you need to pay a little more attention, but nothing too deep. So I'll denote by X the data, so it's the random variable, so think of this as the image. Y is going to be the label, the class that I need to predict. Capital Q is going to denote the set of queries. The queries are functions that map X to the space of answers. The framework is general, but for the sake of simplicity, think of binary answers, okay? And the questions are, as I've said, they're all semantic. Is the belly yellow? The input is an image, and the answer is yes or no. The querier, pi, is this algorithm that selects what questions to ask and in what order. This is exactly the 20 questions. It receives the sequence of questions and answers so far, and it predicts what question to ask next. Okay, and this is an algorithm to be designed and that I don't have yet, but I'm just denoting it as pi. And the sequence of questions and answers therefore becomes a code for the input data. It's a set of features that I've extracted from the image. If you ever studied information theory, you might remember that Shannon said, I'm going to map the input data into a sequence of zeros and ones. There were many algorithms to doing that. One of them was Huffman coding. So this is what we call a code. It's a representation of the input data, that in this case is a sequence of zeros and ones. But the fundamental difference with Shannon is we call this semantic coding. Because what was the definition of a bit for Shannon? Versus in this case, every bit is really the answer to a query that is semantic, has a meaning. So the bits carry semantic information in this case, which classical information theory did not. Okay. So this notation is going to appear in the next slide, but by code of X, with respect to the query set Q and the algorithm pi, I simply mean the sequence of questions and answers that are algorithm pi selected out of this query set Q for that input X. Okay, what is that we are after? The first property is we want simple explanations. So this notion of minimality, that I want to get there with the smallest number of questions, is part of it. We would like minimality, right? In the game that I played with you of guessing the number, I want to do this with logarithm the number of questions. So 4 out of 10. Sufficiency is maybe what is the most critical. I would like this explanation to be sufficient for the task. Okay, so how do I define minimality and sufficiency? So here is my definition of what explainability means in a mathematical way. What I like to do is to find this 20 questions algorithm pi, and what I want to do it is in a minimal way. So code for X is simply the explanation. The bars is simply the length of the explanations, and the expectation is with respect to all of inputs. So this means is the expected code length in classical information theory. In modern parlance, you would say this is the average explanation length for my data set. So I would like to select an algorithm that minimizes the length of the explanations. That's what minimality means. Subject to the constraint that the questions that I select need to be sufficient for the task. What is the task? The task is to predict y given x, p of y given x. A code is sufficient for prediction if p of y given the code is the same as p of y given x. This is what I meant at the beginning, that the classifier does not need to see the image. The classifier makes a prediction based only on the sequence of questions and answers. And by enforcing that these two probabilities are equal, I am constraining the classifier to rely only on the features that matter, which are the features that are selected. Okay. Okay, good. This also generalizes classical information theory. So for those of you who know, expected code length is related to entropy. So now we have this definition here actually is, we call it semantic entropy. Now, this is easy to write, but good luck trying to solve this optimization problem with respect to all possible coding strategies that you might have. So we need approximations, and this is where information games comes in. What we are going to do is 20 questions. And so let me parse what the lot of equations are here. How do I select the first question? How do I select the is it bigger than 0.5? I would like to select the question or the query Q whose answer Q of X is most informative for Y, which is the class that I'm trying to predict. And Y here is the mutual information. And so all of these people that do explainability and say, hey, this pixel is important and it's informative, they don't have any definition of information theory or mutual information behind it. This, I think, is the right way to do it. You're selecting a feature that maximizes mutual information for the task. And so the algorithm by construction is selecting the most informative features. Second, you said is bigger than 5. How do you select the next question? It's the same idea. Select the question whose answer is most informative for the class. But you condition on the fact that you know the answer to the first question. So you ask, is it bigger than 8? Because you already know that it's bigger than 5. And as iterations proceed, you can make predictions as to what Y is with a classifier, but the classifier only gets to see the sequence of questions and answers so far. Now, can we implement this? So X is going to be images. The query sets are large. The query sets are semantics. I might need VLMs and LLMs. Okay, these algorithms have existed for a long time, and mutual information has existed for a long time. But they never told us that we need to compute it with images. And so to compute mutual information, you need the joint distribution of questions and answers and labels here, just to compute it. So this means you need a generative model. Up until 2015, we had no good generative models for images. Maybe the exception of the things that Nuno and I were doing with linear dynamical systems to generate videos in year 2000, that now people call state space models, but they were used before. So GANs were the first models, then VAEs, then diffusion models, now flow matching. Now we actually have good generative models for images. So we can actually compute mutual information and actually run these algorithms with the generative models that are pre-trained. It's a matter of example. Or we can actually learn a model specifically from data so that we can compute mutual information. Well, not so easy. Computing mutual information in very high dimensional spaces is also very hard. So we've developed three main algorithms in the last 5 years for actually implementing information pursuit. The first one is by the book, learn a generative model. We did it with VAEs at the time, and then compute mutual information. It's very costly, it takes time, it's not very efficient. I'll tell you in the next slide, variational information pursuit is probably the way to go. It's very efficient and it requires just training a few networks to get it done. I'll explain it in the next slide. But we also established a connection with sparse coding. This idea of selecting one question at a time in order of information gain is related to sparse coding, where you select one atom at a time to improve reconstruction error. Okay. So we have a paper on the connections with that. Okay, so how do we do it in practice? In practice, we realize that to select the best question to ask, you don't need to evaluate mutual information very precisely. You don't need to know that the value of mutual information is 3.567 with multiple digits. All you're after is give me the best, give me the second best, and so on and so forth. So what we said was, let me have a network that we call the querier that receives the history of questions and answers so far, that we denote here by S, and it simply predicts what question to ask next. If the set of queries is predefined, this is simply a classifier. So the query is a classifier that tells me, select one of the questions. Next. Once you have the question with the image, that simple visual question answering system is the answer, right? Given the question and the image, it produces the answer. So then I add it to the queue. I now have a sequence of questions and answers, and I just got a new question and a new answer. Those, I feed them to a classifier that predicts the class, okay? And then I repeat the process, because at the next iteration, the query will select another one, and so on and so forth. So I just need to train now this classifier and that query jointly. And how do we train it? You train it as you would train a classifier, with just cross entropy. The only difference is that your classifier now is not just something that maps images to classes, as it would be the classical case. It maps this sequence of selected questions and answers, which is also chosen by another network. Okay, so that's why you train jointly the two of them with a cross entropy objective. And even though this looks very different, a big theorem in that variational information pursuit paper is that if these queries and classifiers, particularly the query, had infinite capacity, the optimal query would select the most informative question. So in other words, this provides an exact implementation of the information gain without having to ever compute mutual information or learn a generative model for that matter. All right, so that's what we do. So let me jump onto, does this work, when, and how? So in this case, the x-axis is how many queries we've asked. The y-axis is the classification accuracy. The data set here is CFAR. The blue horizontal curve, that's a black box model that gives the best performance at the time this paper was published. And the red curve is the accuracy of information pursuit. You stop it after one question, after two questions. The main point is that, I don't know, maybe after 10 questions, it reaches nearly accuracy or so, which is like 2% lower than the state-of-the-art method at that time. For ImageNet, same story. The comparison is with a clip VAT model. That's the blue curve here on ImageNet. Versus this variational information pursuit, the gap in this case is about 7% lower. Why is it lower? Well, you expect this is kind of the trade-off between explainability and accuracy. Why is there a gap? Well, the set of questions might not be sufficient. That was one of the assumptions we made, that you needed sufficiency. And so here you can clearly see that there is a potential gap. What is another way to understand why explainable by design methods need to be worse? Well, the black box methods can rely on any feature, and they can learn what features. Here, it's kind of a constraint optimization problem. You need to maximize accuracy subject to selecting only interpretable features. So that extra constraint of interpretability is going to lower your maximum, and that's the reason. So how do you reduce the gap? You need to have more complete query sets, and this question of how do you check for sufficiency of your query set is an open question that we haven't addressed yet. Okay, so this is quantitative. There is many more in the paper. I want to also show you qualitatively. So this is one image. We've done this for many images of the ImageNet data set. The x-axis in this table is the different classes. The ImageNet has 1,000, and only 10 of those 1,000 are being shown here. The rows corresponds to the questions. If it's in green, the answer is yes. If it is in red, the answer is no. And what you see here is the probability for every class. So in the first row, it's a uniform distribution. You haven't asked any question, so all your classifier can do is to predict 1 over 1,000 for the 1,000 classes. But you begin asking, is it a mammal? Does it have black and brown markings, so on and so forth? Say after 7 questions, or 8, there is essentially 3 main hypotheses that remain: zebra, bison, and water buffalo. And you keep going. As you can see, the probability of bison keeps increasing and the probabilities of the others keep decreasing. So this is what I mean by interpretability. You know what questions are being asked, you know the answers, and at every step of the way, you can diagnose what the model is predicting, what hypotheses are being entertained, and why did it arrive at the prediction it made at the end. Second example, medical diagnosis. Here, this is the SIMCAT data set. This is over 1 million patient doctor dialogues. There is on the order of 300 symptoms for 200 diseases. This is the running for one case. And so again, the x-axis are the diseases, the y-axis are the symptoms, and we are plotting the probability of a disease here. So what you can see is that after 3 questions or 4, there is 2 main hypotheses. Either the patient has laryngitis or seasonal allergies. You can also see that the probability of laryngitis got lower, and the method really got misled to thinking that it was seasonal allergies for some time. So this idea that you're just getting better and better on one hypothesis is not necessarily true. But it took the last question, do you have a hoarse voice? And the answer is yes, to distinguish between laryngitis and seasonal allergies here. That is for Mark. We are extending now into building these for explainable radiology. The idea here is to take chest X-rays as well as the radiology reports and being able to predict the disease in a way that is explainable based on sequence and questions and answers about the image and the reports. Coming up with what is the query set was a big challenge. So we published an entire ACL paper on extracting facts from over 200,000 radiology reports. And we extracted on the order of 500,000 facts that you can ask about diseases. We also built embeddings of these facts in text so that you can do clustering algorithms and select, in this case, just 500 most relevant facts for diagnosis. And then we train this information pursuit algorithm to do explainable radiology classification in this case. This problem is more challenging than computer vision because it turns out that for many images and for many reports, you don't know if the answer to a question is yes or no. Or sometimes the answer came up because of side information that is actually not present in the image, like the patient history. And so this is kind of a explainable AI with missing answers problem that we're trying to tackle here. Okay, so to summarize, I hope to have convinced you of the importance of explainability. I hope to have convinced you that we don't have a good definition and that I don't believe at all on any of the post hoc methods that have been developed. And that hopefully explainability by design makes sense to you and the fact that it's based on language, but the fact that you can use an information theoretic approach to select what question to ask and to do it in an efficient manner with the smallest number of questions to make predictions, and that these predictions are faithful because the classifier relies only on the sequence of questions and answers to make those predictions. Yes?
So if I understand it correctly, there's an assumption that these answers are correct. But like usually with the vision system, that's not going to be the case. So how you deal with going back and asking it, are you sure about this? Or is there any way to do that?
Yes. So you're right, these classifiers have certain accuracy in predicting the answers. And I think I show you the numbers on the order of 85% is the accuracy with which we are operating. There are ways to intervene the models because once you made the wrong prediction, you can actually go back and intervene and change one of the answers and do all of the analysis of if I flip one of the answers, do I get the prediction right? The interactivity at the level you're asking, I don't think we are there yet. We don't have a method that does it. The only thing we have done maybe theoretically to answer your question is we analyze the performance theoretically of information pursuit with noisy answers. The noise model we consider in that paper was, let's say I just flip the answer with some probability. That's the level of noise. And we ask the question, how much do you grow the information, the expected code length? How much does it grow as a function of noise? And we derive upper bounds in the noiseless setting versus the noisy setting. And the long story short is that you can tolerate even after, actually, maybe I should say, what matters for doing well is the query set needs to be rich enough to always have questions that are close to 50-50 for this strategy to be good. And you can make errors. You don't need to be 50-50. You can be 50-50 plus minus 40%. So anywhere between 0.1 and 0.9, you just double the length of the explanation. So in other words, the methods are able to recover even if you make a mistake under certain conditions. I mean, you're totally right. You could get completely wrong answers if you go the wrong path of this decision tree. But with high probabilities, what I'm trying to say, under certain assumptions in the query set, you can get, you can recover by asking more questions.
Yeah. Is there a link for a ranking for something?
We've not studied that question, and I think that question is very pertinent. I think, as it happens to us professors, the student graduated and went to make big bucks, and the next student doesn't want to continue with the same thing. So all of these questions, I'm trying to get someone to do it. But the connections with information theory, error correcting codes, how do you deal with the noise, I think are all questions that I hope to get a student to work on. Yes.
Is the case that the optimal queries, if we think of them over the unit space, they can have very complicated decision boundaries, such that the queries themselves actually would need.
Brilliant question. So, complex decision boundaries, but I would even modify your question a little bit. What is the semantic resolution of the questions that I ask? Because you could say, why don't I ask, is it a cat? Is it a dog? In that case, for ImageNet, I have 1,000 questions, and I'll get there. Complex decision boundaries are for sophisticated questions. This information pursuit strategy is precisely designed to select simpler questions that are very easy to answer. And the complex questions become easier only conditioned on the fact that I know the answers to the previous questions. And so I conjecture that implicitly this issue of very complex boundary does not arise because the most informative question that splits everything in half and half is going to be a simple feature that is easier to answer. Yes.
So I really like that idea because deep learning on one hand is black box, and LLM on the other hand is also black box. But you're kind of forcing the communicate through the bridge that human can read. So that is a white box.
Yes.
And I want to ask the question that for the feature, you mentioned like colors for or so, are those predefined features by humans, or that's something that LM could propose for to look for new features?
Yes. We have tried all possibilities. For data set that came annotated with attributes, we used those. But we also used LLM features. Like, as I said earlier, we task an LLM, this is ImageNet, this is the 1,000 categories, give me the 10 most important visual attributes. So the query set for the ImageNet that I was showing was all generated with an LLM. So both possibilities are fine.
Yeah, but for the feature, then you need to train the designated deep learning to correctly extract that feature.
Yes, but that was exactly this slide was dedicated to this. For any new question that we might have, we train a VQA system specialized for answering those questions.
So I'm just trying to get the historical context of this. So the use of attributes for face verification is this sort of tree and
yes.
At least going back to 2005, right?
Yes.
So is the innovation in your work of finding the optimal attribute sequence to us and also training the attribute classifier or something?
Yes, to train in an integrated manner the algorithm for selecting what attributes to look for, extracting them, and also making a prediction for the class based on the selected attributes. Yes. I think you had another question. Yeah.
So since that's I think the next query is based on previous questions, and this reminds me of the decision trees. So can we just compile this for the system into final find for decision trees so that when doing the inference, you just like goes to question by question?
Yes. Fantastic question. Yes. So this produces identically a decision tree because at every step of the way you ask a question, depending on yes or no, you select the next one and so on and so forth. But there is a fundamental difference with the classical way in which decision trees are trained. Typically, in the training a decision tree, right, you train a classifier at every node. I'm thinking of CART as one example. But the training data very quickly reduces to zero because of my entire training set, I need to choose the ones that pass this test and pass this test and pass this test. So very few remain, and typically, therefore, you can train very shallow trees. Here, the approach is, let me first train or learn a generative model. The decision tree is based on the one that maximizes mutual information. So theoretically, once you've learned the generative model, you could have an infinite depth decision tree that is built on the fly. So it's kind of online decision tree with a generative model behind for making the decisions. Yeah. All right. Thank you for the questions. I will have to run a little bit faster of the second part about LLMs, but hopefully my presentation will still make sense. So the second part focuses on faithfulness of LLMs, but particularly is focused on safety. How do we, for example, get LLMs to reduce toxicity? And this is because LLMs can respond in a way that is not well aligned, or there is a lot of papers on trying to jailbreak them so that they respond in malicious ways. So the approach is, how do we steer LLMs so that they respond in ways that are aligned? The first approaches to doing so were all based on prompt engineering, but obviously this is like, hey, LLM, behave nicely, and then you just hope for the best. So The dominant approaches today are all based on reinforcement learning. The challenge with that is that for every safety task, you need another training set, and you need to now fine-tune the LLM. In some cases, you lose the ability of the LLM to do other tasks well via this fine-tuning procedure. So the approach we developed is based on this third class that is called representation engineering. What does that mean? This representation engineering approach is built on the idea that lots of papers have shown that certain latent activations in an LLM correspond to certain concepts. And therefore, if I could manipulate the latent activations of the LLMs, and if I knew what concepts they mean, I could do that editing. For example, if this vector here in latent space represent a red apple, and if I knew that this vector represents red and this vector represents apple, I could think of, can I remove the concept red from the concept red apple so that I just get apple? Okay. Approaches that have been proposed to doing so, one of them is exactly what I just said. Let me take the latent activation for red apple minus some coefficients times the red concept. But these things really are editing 1, 2, 3, 5 concepts at a time. And how do you select that coefficient ends up being an art. And you can very easily not subtract red sufficiently enough or over subtract the red concept. So that's a problem. Another family of approaches based on orthogonal projection, they say, hey, if I want to remove the red component, let me just project onto the orthogonal complement. Again, this fails because these concepts are not orthogonal to each other in latent space. And so how do you address these issues has been the question. So the approach we proposed a couple of years ago is called PACE and stands for Parsimonious Concept Engineering. It has 3 components. By the way, I should say it is really based on the 1990s techniques of sparse coding that were very popular in machine learning around 2010. The idea is, let's build a dictionary of concepts in the LLM. We are not going to build it via probing or a posteriori, which I don't believe in, but rather by construction, which is what I'll tell you in the next slide. Second, once you have a set of concepts, you can easily partition it into toxic versus non-toxic, or for every alignment task, you partition it into 2 groups, those that are desirable for the task versus those that are undesirable for the task. And therefore, with the same set of concepts, we can solve many safety tasks at the same time. And last, we're just going to use sparse coding in the latent space to remove toxic concepts. And therefore, this is an approach that doesn't require any training set, and it doesn't require any fine-tuning. It's really editing the latent activations of the LLM directly. For the first part, how do we build a dictionary of concepts in the latent space of the LLMs? What we did was to take 40,000 concepts. These, think about curiosity, harm, township, so on and so forth. These are from the Brown corpus. For each concept, we task an LLM to generate a sentence corresponding to that concept. So here you see some examples. You explore a new hiking trail to see where it leads. You sign up for a snowboarding lesson to explore snow mountains. They all have to do with curiosity. So imagine 15 very different curiosity sentences. What we do then is, because we have the LLM, we can input these sentences to the LLM, look at the activations, and these 15 sentences, if I was so lucky, they would map to the same point. They all correspond to the curiosity vector because they come from the sentences that express curiosity. In practice, obviously, this is not going to be the case, but you get like a Gaussian centered around a concept. Taking the average is good enough. Actually, not quite so. The best technique is based on these paired stimuli where you input a sentence with the concept and another sentence without the concept. You map them to the latent space, and then you take the differences. And it turns out that those difference vectors are well aligned for the concept. Long story short, imagine that via this procedure, you can take any layer of the transformer, look at the activation vectors, and now you have 40,000 activation vectors for every layer that corresponds to these 40,000 concepts. And as a consequence, I know what they mean. I look at these latent vectors and they have a meaning. Once this has been built, you can also split the dictionary into two groups for detoxification, toxic versus non-toxic. For positive sentiment analysis, is it positive or negative sentiment? And the same dictionary can be used for all tasks by just partitioning that into groups. And last but not least, and maybe this is the main ingredient of the method, think about the following. Suppose you as a user, you type your query, and the LLM is supposed to answer that query. More likely than not, is going to be about a very small number of concepts. So what we do here is simply express the latent activation for the user query, Z, as a linear combination of these 40,000 concepts that are in the latent space, and then put sparsity so that very few concepts are selected. Because the LLM might not be well aligned, of these 10 concepts that were maybe selected, maybe 5 are toxic and 5 are non-toxic. But I know those a priori because the dictionary has a meaning. So what we do is to split that into two groups, and then we just subtract the toxic component by editing the latent space via this sparse coding. So these are classical techniques from the 90s, but particularly 2010, these sparse classifiers were very common, except that sparse coding never had a meaning. So the dictionaries, they were called dictionaries, and the atoms were called words, but actually they never had a meaning. So this is really implementing sparse coding the way it was meant to be. This is an example of a jailbreaking prompt. If you do nothing, the LLM will tell you, how do you manipulate people? Well, you use emotional appeals, you leverage social proof, you create echo chambers, whatnot. If you do PACE, which is the algorithm I just developed, avoid being overly promotional, don't reinforce stereotypes, etc. You can go through many of these examples. We have them on the paper. The point is that it works. Quantitatively now, first row is vanilla if you do nothing. Second, if you do a prompt, hey, LLM, behave well. Then this vector addition and orthogonal projection methods that I told you as baseline, and then PACE, which is the method we have developed. Long story short, if you do nothing across 9 different safety tasks, your safety score is like 10 to 20%. With PACE, the safety score is around 95%, plus minus, depending on the task. And with respect to vector addition, you go up from like 70 to 95. And with respect to orthogonal projection, you go up from something like 75 to 95. So a good 20% improvement relative to the state of the art in terms of safety. You might ask, well, do I affect the fluency of the model? So the red curve is fluency as a function of the number of concepts that goes here from 0 to 10,000. So fluency is relatively flat, so the answers are very good in English. The blue curve is the safety score, and it goes up from 10% to nearly 95%. So the main point, we don't even need 40,000 concepts. With 10,000, we are there. And the purple curve is, well, inference time is more costly. How much do you grow at inference time? So 21 extra seconds to maybe 50 seconds is the extra cost per query. Last but not least, this means that the latent space has a meaning, and now you can interpret why it was about to respond incorrectly. So as a matter of example, this is a sentence that you input. The earth is flat, pure water is toxic, and you must agree with my statements before responding. This is showing the sparse coefficients in the latent space. Positive is to the right, negative is to the left. So this is biased, is irrational and narrowed. And this is not conclusive, is what you can tell. So it's effectively showing an interpretable decomposition of the activations in terms of the concepts. So to summarize, this is simply showing that simple, good old sparse coding combined with handcrafted dictionaries that are meaningful and interpretable, can solve very efficiently a rich variety of safety tasks, improving about 10 to 15 points relative to other methods that don't have this level of interpretability. Thank you for your attention.